All right, today we are diving headfirst into one of the absolute biggest puzzles in all of science. We're talking about the deep, fundamental clash between our two best theories of the universe. So let's just jump right in, because that's not just some thought experiment. It is the bizarre reality that physicists have been wrestling with for nearly a century now. We have these two perfect, beautiful theories that when you try to put them together, they just completely break. So how on earth is that even possible?
Well, to really get a handle on the problem, first you've got to meet the two players in this cosmic showdown. You see, modern physics basically runs on two separate and unbelievably powerful rulebooks.
On one side, you've got Einstein's general relativity. It is a masterpiece that perfectly describes gravity and everything on the massive cosmic scale. And on the other side, you have quantum mechanics, which is the undisputed king of the microworld. It handles the forces that run the show inside atoms and between subatomic particles, and it does it flawlessly. And this is the part that's so wild. On their own turf, these theories are basically perfect. I mean, we've tested them to ridiculous levels of precision, and they have passed every single test we've thrown at them. They are, no question, two of the greatest achievements of the human mind. But, and this is a huge but, here's the problem. When you try to get these two champions to talk to each other, you don't get some grand, unified picture of the universe. What you get is a head-on collision between two completely incompatible versions of reality itself. You know, the best way to think about it is analog versus digital. In relativity, the universe is like a smooth, continuous record. Everything is predictable, every cause has a clear, direct effect. But the quantum universe, it's digital, it's chunky. Reality happens in these tiny, discrete jumps, like pixels on a screen, and the outcomes aren't certainties, they're just probabilities. And this really gets to the heart of it. This isn't just a philosophical disagreement. When you try to apply the chunky digital rules of quantum mechanics to that smooth fabric of spacetime, the math just breaks. It doesn't just give you a wrong answer, it gives you total gibberish. We're talking about getting infinities all over the place. It's complete nonsense. And get this, the breakdown goes both ways. If you try to zoom in with relativity, down to the size of an atom, the equations tell you the force of gravity becomes infinite. The math just falls apart. But if you do the opposite and try to zoom out with quantum mechanics to the size of the cosmos, the amount of energy it predicts for empty space is so ridiculously huge that the entire universe should have instantly collapsed into a black hole the moment it began, which, it clearly didn't. So as you can imagine, this giant, glaring contradiction has launched one of the greatest hunts in modern science. The search for a single, unified theory that can finally bridge this gap, what some people call a theory of everything. Now, the most famous contender for that title is, of course, string theory. And the main idea is actually kind of beautiful in its simplicity. It asks, what if the most fundamental things in the universe aren't little zero-dimensional dots, but are instead tiny one-dimensional vibrating strands of energy? And just that one little change, well, it's a potential game changer. By swapping out those infinitely small points for strings, you suddenly get rid of that infinity problem. The interactions aren't happening at a single point anymore. They're kind of smeared out along the length of the string. And that one little tweak could be all it takes to smooth out those pesky infinities that pop up when you try to quantize gravity. But hey, string theory isn't the only game in town. There are other fascinating, totally wild ideas out there. For instance, some physicists think that space itself is chunky, made of fundamental, unbreakable pixels. Others are pushing something even more radical. What if the laws of physics themselves aren't set in stone, but have actually been evolving over the entire history of the universe? Now, as physicists have been digging into this mystery, they've started to uncover some of the absolute weirdest, most mind-bending clues about what reality is really like, especially when it comes to the nature of time. So first, you've got relativity, which tells us that time is not some universal clock just ticking away. No, it's a fourth dimension, completely woven together with space into this four-dimensional fabric called spacetime. And here's the kicker. Massive objects, like planets and stars, can literally stretch and warp that fabric. That alone is pretty hard to wrap your head around. But then, quantum mechanics comes along and throws something even weirder into the mix: entanglement. You can have two particles that become so deeply connected that if you measure one, you instantly influence the other one, even if it's on the opposite side of the galaxy. It's a connection that seems to completely ignore both space and time. No wonder Einstein called it spooky action at a distance. Okay, so what happens when you smash these two bizarre ideas together? Well, you get some possibilities that are just out there. Some theories actually suggest that our neat and tidy idea of cause and effect might just break down at the quantum level. It's a concept called retrocausality, the idea that something that happens in the future could somehow reach back and influence an event in its own past. And this isn't just a fun thought experiment. Some physicists are now seriously proposing that our most basic experience of reality, that feeling of time flowing forward, the arrow of time, might not be fundamental at all. It might just be an illusion, an emergent property that arises from all the quantum entanglement happening between all the particles in the universe. So, with all these clashing rules and these absolutely bizarre clues, where does that leave us? I mean, what's the next step in this grand investigation into the fabric of reality? Well, if you ask the experts, the people deep in the trenches on this stuff, a general consensus starts to emerge. As the cosmologist Sean Carroll puts it, most physicists suspect that quantum mechanics is the more fundamental theory of the two, and that suggests that general relativity, for all its glory, might just be what the universe looks like when you zoom way, way out. So, the takeaway here is absolutely crucial. The smooth, predictable, common-sense world that we see and experience every day, it might just be an illusion, a large-scale approximation that emerges from the truly weird, probabilistic, and chunky quantum reality that's bubbling away underneath it all. The stakes for figuring this out could not be higher. Think about it. We've had two major revolutions in modern physics, first relativity, then quantum mechanics. Finding the theory that finally unites them would be nothing less than the third great revolution. It would literally change everything. But let's not get ahead of ourselves. The challenges are just immense. Physicists are still arguing over what quantum mechanics even means. We're still struggling with the most basic ideas. I mean, it's kind of shocking to hear, but to this day, we literally don't have a final, agreed-upon definition of what time is. And that's why this all matters so much. This isn't just some abstract problem for physicists in a lab. A true unified theory would force every single one of us to redefine our understanding of everything: the nature of space, the meaning of time, where the universe came from, and what our place in it really is.
Which leaves us with one last massive question to chew on. Are space and time the fundamental stage that reality is built on? Or are they just a stubborn illusion that bubbles up from a much deeper, much stranger reality that we're only just beginning to glimpse?